at the postsynaptic membrane where neurotransmitters bind to their chemically gated channels. The blue arrows indicate the migration of the graded potentials. And let's assume that our graded potentials are primarily depolarizing graded potentials. In real life, they're going to be a mixture of depolarizing graded potentials as well as hyperpolarizing potentials. But so where they are generated here, remember they're going to move away from the axon and towards the axon, across the surface of the cell body, etc., etc. So ultimately, the chances are great that the graded potentials will be such that by the time they arrive at the axon hillock, which is right about here, that funnel-shaped area where we begin to see voltage-gated channels. All these circles are my voltage-gated channels. By the time our graded potentials begin to arrive at the axon hillock, the hope is that they will manage to summate, that is, all their voltages will add up to where they will indeed change the resting membrane potential from -70 to -55 millivolts. In other words, a change of about 15 millivolts. And this change of about 15 millivolts is the change in voltage that is needed to open up the first few sodium voltage gated channels. And of course that leads to the influx of sodium through the voltage gated ion channels, and this then leads to the firing of our action potential. What we now need to still do is learn exactly the details of an action potential. That is, we now learned that the sodium voltage gated channels open, but you've known for a while already that somehow the potassium voltage gated channels are involved as well. And you also still need to learn how action potentials propagate down the axon. So we'll do that in the next video clip.